Katie works with Leah Somerville in the Department of Psychology at Harvard University. And her work overall examines how ongoing brain development during adolescence influences behavior related to motivation, learning, and cognitive control. And Katie is an NSF Graduate Research Fellow, and she's also an award recipient from the Sackler College Program in Psychobiology. And very recently, Katie actually defended her dissertation 1 week ago.
I haven't printed yet, so I submitted the document.
Okay. Still, that's amazing. We're so glad to have her here today. So please join me in welcoming soon-to-be Dr. Katie Insel.
Okay, so I'm going to start the screen, and you see the slides, okay?
Mm-hmm. Perfect.
Great. So some of my work is going to be pretty new. So I know that usually these talks are kind of and I know that Leah was really sick, so she's not able to make it for the program, but I think she's coming later in like a few months. So hopefully this is a nice preview of some of the research you might see again. And I'm also happy to have you guys interrupt at any point if something's not clear, if you have questions. Yeah, any other ground rules or anything I should know, or can I just go ahead and get started?
No, I think you've got it all.
So my examining how goal-directed behavior, which we can think of as a process of how we orchestrate our actions in pursuit of a prospective outcome. I'm really interested in understanding how that type of behavior changes over the course of adolescence. So just to get everyone on board with the type of behavior I'm interested in, I'm going to walk you through a quick example. Whoop. Sorry, making noise on my end. So I really enjoy going to a developmental cognitive neuroscience conference, and I recently got the notification that this year's abstract is due April 1st. So I have about a month to put together an abstract. And you can imagine that the way I behave and the way I organize my actions leading up to that deadline is going to influence whether or not my abstract gets accepted. And there might be different stakes at play that sort of govern my actions during this time. So you can imagine if I'm submitting for a poster presentation, I might not prepare that far in advance. I might put in a little bit less effort. I know that based on my experience in this conference before, poster presentations tend to be accepted. But you can imagine that my behavior might change if I was submitting for a more high-stakes situation. So if I was putting together an abstract for a talk, I might work harder, put in more time. I might kind of put in as much effort as possible to make it the best abstract to increase the chances of it being accepted so I can go to the conference. And these types of behaviors have been studied a lot in adulthood. And prior research in adults has shown that individuals typically increase and enhance their goal-directed behavior when they're in high-stakes situations. So this is an example of a motivated group task where participants there was different rewards at stake based on different trial types. And what essentially I'm showing you here is that when there was reward at stake for their performance, overall adults selectively improved how well they performed on the task. There's kind of a growing body of this research in the adult literature that has also conducted these studies in conjunction with functional neuroimaging. And the vast majority of studies have implicated a corticostriatal circuit in supporting. So we can think of these stakes-based improvements that we observe in the behavior to be guided by coordinated recruitment of this network. So we can think of it as this network is sort of orchestrating how well I can adjust my behavior in the moment in conjunction with in the adult literature is when participants are doing tasks like that rewarded group, they actually increase recruitment of this circuit and often show enhanced functional connectivity within it. And we can kind of ascribe some sort of functional roles to subregions within the circuit. So the ventral striatum is canonically associated with detecting the value of cues in the environment and also registering the value of outcomes. The dorsal striatum is more canonically associated with coordinating action selection and motor outputs. And the striatum can relay value and action-related information to the prefrontal cortex, which is thought to coordinate the execution of goal-directed actions and especially control. So these systems are interconnected through a really large distributed circuit. Here you can see in the colors, the orange and yellow and green denote the patterns of functional connectivity. So there's different subregions within the striatum and the prefrontal cortex that share direct connections, but there's also loop projections throughout that allow these regions to communicate, sometimes indirectly. And again, like I was saying, functional connectivity within this network has been shown to really support these sort of value-guided boosted performance. Interestingly, this circuit also changes over the course of childhood and adolescence. So this is a really basic kind of circles and arrows schematic of how connectivity within the striatum and between the striatum and prefrontal cortex is changing with age. So what you can see here is that the connections with sometimes have a dotted line, which represents a weak connection or a non-significant connection, or a solid line, which would represent a significant connection in functional connectivity. These connections are changing over the course of development. And so essentially there's a refinement that's going on. So what you can see is in the transition from childhood to adulthood, there's strengthening between the dorsal striatum and the ventral striatum, but also between the dorsal striatum and prefrontal cortex. So this kind of enhanced connectivity profile is coming online. But then in the transition from adolescence to adulthood, you actually see a refinement. So now there's weaker within striatum coupling, but enhanced coupling between the prefrontal cortex and dorsal striatum, which suggests there's sort of this preferential component of the circuit that's now being selected during behavioral tasks. So as a result of these ongoing changes that are happening over the course of adolescence, we can think of these shifting connections as representing potential key changes within nodes that communicate with each other that may have. When it comes to behavior, we can think of adolescence as broadly a time when there's a lot of normative shifts in both motivation and cognitive. Period when adolescents are steadily maturing and their cognitive abilities are kind of improving gradually as they age. So in one sense, teens are performing cognitive tasks better than they ever have in their lives, but they're also still continuing to show developmental improvements as they approach young adulthood. But it really remains kind of unclear right now in the literature whether adolescents can adjust the exertion of cognitive control when there's different motivational incentives at stake. So what I'm hoping to show you today is how, over the course of adolescence, the ability to use value to adjust behavior in a goal-directed fashion changes. So I'm going to present two studies. The first is an fMRI study examining incentivized cognitive control over the course of adolescence. And then I'm going to switch gears and talk about the domain of reinforcement learning and consider kind of how these value interactions may manifest in adolescence in kind of a different domain. Okay, so for the first study, what we did is we designed an incentivized go-no-go task. So this is kind of a classic go-no-go cognitive control task where we're just adding a stakes manipulation. So if you're a participant in this task, you're told that first you'll see a cue before you begin to participate. You might see a cue with 1 star, and that means that whenever you're correct, you could earn 20 cents, and whenever you make a mistake, you could lose 10 cents. In the high-stakes situation, participants first viewed a circle with 2 stars before encountering a series of trials, and this meant that they could earn $1 for every correct action or incur a loss of 50 cents for every error that they made. So in the task, first they'd see the stakes cue telling them how much they could earn, and then they're presented with different target types. So in this example, if they saw a planet with craters, this counted as a go target. So they're told press a button as fast as you can. But if you see a planet with stripes, the instruction was to withhold a response. So the planet with stripes here serves as the no-go cue. And the way that the trials unfolded is first you'd see a cue, and then you'd be shown a series of go and no-go trials in kind of blocks of 8 targets, and then at the end you'd receive performance contingent feedback. So this is an example of a low-stakes block. So this means I could win or lose the low amounts. And so if I was participating in this task and I went ahead and made a button response for each of these stimuli, what I would essentially earn is 20 cents for pressing for the go trials, because that's the correct thing to do. But I'd actually, if I made an error and pressed for a no-go trial, I would be penalized and I would lose 10 cents. And the earnings were cumulative over the course of the task, so participants are incentivized to try to do it the best that they can. So this is an example of a high-stakes block, or sorry, a low-stakes block. The high-stakes block looked virtually the same. So the visual and cognitive demands here are identical. The only thing that's different is that initial cue that's telling them how much they can earn, and then kind of the incentives that are associated with the action contingencies. But really, almost everything that they're seeing and motorically what they're preparing for is identical, except for the incentives that they're working towards. Any questions about the task? Yeah.
Yeah, so I haven't seen this type of planet task used before. This is really interesting. I'm curious if, like, from like a more traditional, like, go no go standpoint, if their performance is decreased just because the stimuli in the two conditions, I think, are maybe a little bit more similar.
Yeah. So what we did is we chose kind of a textural property for the discrimination. We have versions of go-no-goes. The lab has done of many different types of varieties, but we've used stimuli like faces, where people discriminate between male and female. Some people use things just like colors. Here, what we wanted to do was have sort of an overall rule. So the planets provided kind of a textural feature that people could detect, but it's not. It does take discrimination, and we included different we have different exemplars within each category, so they're not seeing the same image over and over again. And we did that on purpose to kind of avoid the habituation to the stimuli and the possibility of repetition suppression and the scans that we acquired. So this might be more challenging than if we just show them like red and blue images because of the textural feature. But I don't have the same participants doing like a more basic go-no-go design. Another thing I should just mention too is that we vary the prepotency throughout the task. So sometimes you might see one go before a no-go, another time you might see 2 or 3, and that prepotency component also makes it a little bit more difficult, because the idea is like if you're going, you have this motor prepotency, which makes it actually harder for you to stop. So we try to sort of leverage this,
The HDMI just disconnected for a second.
Yep, hold on just a moment, Katie. We're having a little bit of an AV problem.
Okay, maybe it was loose.
I think we're back. So I think we missed just the last part of your explanation of the go-no-go task.
So basically, they're experiencing low and high stakes blocks throughout, and you're interested in comparing performance across these conditions. So for the participants, we had 88 participants from the ages of 13 and 20 participate in the study. Because of motion and quality issues with the upper prime data, so younger participants just tend to move more, and developmental recruitment, that's one of the big challenges that we face. But we wanted to make sure that motion and kind of quality related confounds were going to be an issue in our MRI analysis. So we excluded a subset of the participants who had really noisy data. So today when I show the MRI results, it will just be in a subset of the sample of 72. Okay, so when we're looking at performance on the go-no-go task, what we do to measure overall global performance is compute an index of D prime. So what D prime is telling us, it's how often you're going when you're supposed to go, and then you subtract out how often you press to those no-goes when you're not supposed to. So it's basically like the hit rate of how good your go accuracy is minus how often you fall. So kind of a global discrimination score. And what we did is we plotted go-no-go performance with D prime continuously with age. I'm actually going to bin our ages into subgroups today just to have an easier visualization, but we use age as a continuous predictor in all of our analyses. So this is the low stakes performance. And what you can see is that as participants get older, there's a steady increase in this D prime measure. So this is very consistent with the fact that cognitive control abilities are continuing to improve across the course of adolescence. And this is something that we see in the broad literature. Adolescence and early adulthood. But what we're really interested in is how people are performing in those high relative to low stakes conditions. So if we look at our 19 to 20-year-olds, we see that there is a significant increase in performance for high stakes relative to low stakes. And this is consistent with some of the earlier work I was talking about in my introduction, which has shown that broadly, young adults tend to improve cognitive performance when they're was when we looked at our younger age groups, between the stakes conditions. So they were performing comparably whether a low or high stake incentive was at play. And this was a significant age by stakes interact. While the adults are improving in high stakes situation, the adolescents are performing comparably, which may represent an inability to integrate the stakes context or this value cue with the execution of control in the moment. So we were really intrigued by this finding, and we wanted to understand doing or not doing that may explain why they didn't benefit from the high stakes situation. So to really dig in, we interrogated several potential psychological and neurocognitive processes that may account for this pattern in age-related change that we observed. So the first thing we thought, well, maybe the adolescents across the ages value the incentives differently. So what if those older adolescents and young adults are improving because they simply value what's at stake more than the younger ages? So this might be kind of an uninteresting confound. To test for this, what we did is we showed all the participants the different monetary outcomes that were at stake and had them rate their subjective experience of how good or bad they felt and how intense that feeling was when they received the different outcomes. And we also had them rate the task stimuli to get a sense of if they really represented this differential in the value stakes when they were seeing those cues in the arousal scores, the self-assessment mannequin. And what we found was that there was no relationship with age, either main effect in terms of rating or in those interactions. So what this means is that all the participants across positive and higher in arousal than those low stakes cues. And they were also similarly ranking the monetary outcomes at stake. So this lent some confidence that it's not just a baseline subjective value difference in how they're perceiving or liking these monetary incentives. We also were able to look at functional recruitment in the brain during the stakes cue. And this would basically ask the question of when you're seeing this cue that's telling you you're about to engage in this cognitive task, are you recruiting regions differently when you're anticipating a high stakes block of trials versus a low stakes block of trials? So if you're in this part of the task as a participant, this is just passive viewing. There's nothing motor going on. It's just telling you how much you could receive in the upcoming trials. And so we did a whole brain contrast, and this is collapsed across all of our participants. And what we see is that across the age groups, there was really robust increased recruitment of the ventral striatum as well as prefrontal cortex when they were viewing those high versus low stakes cues. So this suggests that there's this corticostriatal upregulation that's happening during the cue period that may be helping them prepare for the trials, but there's not a difference with age. So this was consistent in our younger and older participants. So this kind of ruled out the possibility that maybe there's a different preparatory kind of value process that's going on during that cue period. But what we wanted to know was, well, how is this kind of selective value signal in the ventral striatum during that cue period propagating to the rest of the brain during the task? So if this preparatory period is gearing you up to participate, are you going to use this value signal to then selectively increase or decrease recruitment during the task itself? So what we did is we ran a functional connectivity analysis to test this. So we set a seed region within the ventral striatum, and then we ran a PPI analysis to find the regions in the brain that were temporally coupled with the striatum. So basically what this is going to show me is in my contrast, where is activity correlated over to striatum. So we can think of this as sort of a proxy for like network coherence. We ran the PPI specifically for the contrast of high stakes versus low stakes. Those high go-no-go trials versus those low go-no-go trials. And we only modeled trials that were correct to make sure that we were tapping into when participants were actually performing the task accurately. So we were interested in this connectivity profile, how it was changing as a function of both age as well as behavior. So to do this, when we ran our PPI analysis, we as a whole brain covariate to identify what connectivity that was increased for high stakes is also related to increased high stakes behavioral performance. So to do this, we just had the D prime for high and we subtracted out the D prime for low and had this different score. And when we used it as a covariate, what we found was that the individuals who were doing better in high stakes showed enhanced coupling between the ventral striatum and the VLPFC, the ventrolateral prefrontal cortex. So this basically is telling us that the more you boost performance in high stakes, the more likely you are to increase connectivity between the striatum and prefrontal cortex during those high stakes conditions. And this reveals a potential mechanism of how individuals are enhancing performance during the task. And it really suggests that the importance of connectivity and observing these high stakes improvements. We also wanted to know how connectivity profiles were changing with age. So to do this, we did a similar analysis using a whole brain covariate, but this time we used age to look at how connectivity was changing as participants got older, as well as how connectivity was changing as participants, what was kind of decreasing with age. So first, what I'm going to show you is connectivity that was stronger in participants that you were to show connectivity between the ventral striatum and the lateral prefrontal cortex during high stakes conditions. So this is similar to what we saw with behavioral improvement. If we look at the other patterns, so what's decreasing as you get older, we found that in our younger participants, during high stakes, they were more likely to show coupling between the ventral striatum and the dorsal striatum. So you can think of this as kind of within striatum coupling, whereas as you get older, striatum just showing more long distance connectivity between the striatum and the prefrontal cortex. So this suggests that there's kind of these shifts with age from short range connections to long range connections that might be related to the performance that we observed. So as I showed you, that changed with age, and it really mirrored the pattern that we saw in behavior. So these connectivity profiles that are increasing with age are also increasing based on how well you boost performance in high stakes conditions. So we ran a conjunction analysis to identify the areas of overlap, and indeed there was a significant cluster within the ventrolateral prefrontal cortex that was related both with this different score as well as age. And so what we did is we conducted a formal mediation analysis to ask, well, is this connectivity profile mediating the initial relationship we saw between age and this high stakes boost in performance? We found that the mediation was indeed significant. So if we take into account profile, it accounted for about 43% of the behavioral relationship that we observed. And so this suggests that connectivity is mediating the high stakes improvements with age that we measured in behavior. So just to quickly summarize, for study 1, we found that value selective cognitive control is emerging in late adolescence, and this behavioral expression may be explained by ongoing development of this functional recruitment within the corticostriatal network. So next I'm going to switch gears to a different fMRI study. This is looking at, instead of cognitive control, at reinforcement learning. So I just want to take a pause to see if there's like interim questions for study 1. Okay, so I'm going to switch gears. So in study 2, what we really wanted to know is we see this behavioral profile with this late adolescent emergence of kind of these value benefits and behavior in cognitive control, but do these patterns generalize across different cognitive domains? So I switched gears and tested a stakes paradigm using a reinforcement learning task. So just to give you a really quick summary, prior work in young adults has shown that when encountering a reinforcement learning environment, if high stakes incentives are at play, adults become more accurate when they're learning, and they not only become more accurate, but they actually become more strategic. So they'll exert more but when it comes to developmental changes within this ability, we don't really know when individuals gain the capacity to make these sort of stakes selective behavioral changes. So we designed a study to test this. We used a classic reinforcement learning task that involved cueing different shapes with probabilistic contingencies, and we simply added a stakes manipulation to this. So essentially what happens is if you're a participant in this task, you'll be shown a choice. So here it's 2 fractal images, and we just ask participants to choose a button to either choose the shape on the left, so the pink shape, or the right. So let's say here I'm a participant and I'm choosing the green shape. On about 75% of the trials, I'll earn a reward of 50 cents. But on a rare 25% of the trials, I actually won't earn anything. So I'll get a reward of 0. So what this means is that overall, through the course of the task, this is the optimal choice because it's the choice that yields the best outcome on the majority of trials. The probabilistic contingencies were linked. So if instead of choosing this green shape, I chose the pink shape, what would happen is about 75% of the trials, I would get the unfavorable outcome of $0. But on the rare 25% of trials, I would earn that 50 cents. And so what this means is that basically the pink choice in this example is the suboptimal choice to make because most of the time when I choose it, I'm not going to get the best outcome. And these probabilistic contingencies allow us to look at incremental learning over time. So the fact that it's not deterministic, so not every time I make that choice I get the reward, allows us to look at how people are shifting their behavior in response to the feedback. So what I just showed you is an example of a high stakes trial. Participants also had low stakes trials where similarly the choices were probabilistic, but this time if I made the optimal choice on the majority of trials I could get 25 cents, whereas on the 25% I'd get nothing. And if I made that suboptimal decision about 75% of the time, 25 cents. So the behavioral measure of interest here is how people are using the feedback they get over time. So for this task, we had 84 participants from the ages of 13 to 21 again, who participated this time for the behavioral sample as well as the imaging sample. So what I'm going to show you first is what we can think of as a proxy for accuracy on this task. So this is the proportion of time that participants are choosing that optimal choice. So we call this proportion optimal choice. So it's basically saying how often are people choosing the picture that was rewarded the most frequently. Again, I'm going to show you binned ages for displaying the trend, but we did all these analyses continuously. So if we first look at our 19 to 20-year-old group, we see again that there's this is increased incentives. But if we look at our younger ages, they're not discriminating between low and high stakes. So this suggests that while the older participants are improving,
Hold on just for a second, Katie. We're having another AV issue here. Is the display actually turned off?
Yeah.
All right, I think we're back in business. Sorry about that. I think we just hit we've got these brand new TV monitors installed in all of our conference rooms, and they have these like timer limits that I think that are not being picked up on by the way that we're presenting today. So thanks for being so patient. I think we heard about the difference in the 19 and 20-year-old group, but the rest is new to us.
Yeah, great. So the 19 to 20-year-olds show this stakes difference, but when we look at the younger ages, they're not discriminating performance between those low and high value conditions. So what this means is that essentially the ability to sort of make these value selective performance adjustment seems to emerge as adolescents get older. We also had all the participants rate the monetary incentives in the different task cues, just like we did in study 1, and it wasn't differences. We couldn't explain this effect when we controlled for those subjective value ratings. So the ratings were consistent across age. It's really how they're using those value incentives to update performance that seems to be changing. So for this task, they performed the task during fMRI scanning, and what we were able to do was look at the outcome period. So here I'm going to show you a contrast of when participants are receiving feedback after their choice. First, I just wanted to identify activity that was selective to winning a reward versus winning nothing. So this is across all participants. It's a whole grain contrast of that winning versus winning nothing feedback. What we found was that when participants won a reward, whether it was 50 cents or 25 cents, versus when they won nothing, there was really robust recruitment in the bilateral ventral striatum. But the question that we were really interested in is how is this activity changing as a function of stakes over the course of age in adolescence? So to do that, we defined an ROI in the ventral striatum using the Harvard-Oxford Atlas, and we extracted the beta parameters for the events when participants won the high gain feedback, so those 50-cent wins, as well as when they won the low gain feedback, so when they're getting 25 cents. So what I'm going to show you in the plot is the age plots of the fit. So basically what you see is that there's no difference with age when you look at striatal recruitment in the low stakes condition, but for the high stakes condition, that recruitment increased as participants got older, such that the older adolescents were showing this kind of stakes discrimination in these striatal outcome recruitment patterns. So what this means is basically the older you get, the more you differentiate between these high and low rewards in the striatum during this outcome period. So this pattern of age-related brain activity paralleled the behavioral interaction that we found. So our next question was, well, is this difference in striatal recruitment for high stakes versus low stakes outcomes related to how likely you are to differentiate performance in the task? And so what we did is, again, we used the same ROI, but instead we took the contrast for high win versus low win. So this is the contrast of winning 50 cents versus 25 cents. And we ran a regression to try to see if we could relate it to those behavioral differences. So what I'm showing you on the y-axis is a difference score for high stakes learning performance versus low stakes learning performance. And we found that the individuals who increased recruitment for high versus low outcomes in the ventral striatum were more likely to increase performance in those high relative to low learning conditions. So this suggests that this high stakes selective recruitment in the ventral striatum may enhance a high stakes prioritization during learning, during the behavior. So just to quickly sum up, what we found is emerged in late adolescence, and this behavioral effect was supported by age-related shifts in value selective recruitment of the ventral striatum that also in turn accounted for behavioral change. And so just to conclude broadly, overall what we're finding is that younger adolescents, they report valuing high stakes incentives just as much as older ones do, but they're not using that valuation to selectively adjust cognitive control performance. This is also similar in a learning domain. So when individuals are learning from incentives, late adolescents exhibit these high stakes improvements, but we don't see this effect in younger ages. And the data that I showed you today provides some evidence that there might be something about the late refinement of functional coupling within corticostriatal systems that may kind of set the stage for the successful value-guided cognition that we observe in our older individuals. And these shifting profiles in value-guided cognition may modulate goal-directed behavior across adolescents in different ways. So when we take a step back and think about how to incentivize performance and the different kind of challenges that adolescents face in their daily lives, suggests that incentives may kind of manifest differently depending on an individual's developmental stage. And that is it for now. So my advisor is Leah Somerville. She was involved in all these studies, and I also had a huge team of research assistants who helped with all the data collection, and some of them helped with analysis. My lab has been extremely helpful. That's a picture of them, and I also supporting this research. And I'm happy to ask questions of you, but also answer any questions that you have.
All right, fantastic. Let's thank you. go ahead and open it up to open questions.
So I have a question. Going back to one of your earlier intro slides where you were talking about the connectivity between how it changes from childhood to adolescence to adults. So I was kind of curious. So you just generally refer to connectivity between the that slide exactly, yeah. So you generally refer to just the prefrontal cortex, but I wonder if where in the prefrontal cortex also changes as a function of becoming adolescent to adults. So I'm not really familiar with this literature, so what would some of the changes be? Where would it change?
Sure. So this particular example was looking at connectivity with the right inferior frontal gyrus. So this is taken from a paper that Via Somerville published in 2013. Cats with older response if they saw a smiling face, but to make a button press if they saw a calm face. So similar go no go like what we tested, and what they found, and this is pretty typical across these go no go response inhibition tasks. Age gradient, but this particular study that I'm showing data only looked at connections with the lateral prefrontal cortex. But there is a lot of work in kind of the emotion regulation literature showing that there's these sort of subcortical connections with medial prefrontal cortex seem to come online earlier in development than the connections with lateral prefrontal cortex. Yeah.
So I noticed in your reinforcement learning finding that it looked like the 17 and 18-year-olds, although they were not discriminating between high and low stakes, that the low stakes condition may have been had higher accuracy than the 19 to 20-year-old condition. I was just kind of curious if that was a significant difference there between the low stakes in those two age groups, and if there's anything that we can kind of make of that.
Sure, yeah. So the quick answer is that despite appearances, it was not significantly different. I think the thing that's interesting is that you're seeing, so if you look at the two green bars in the 17, or they're all green, but the darker green in the 17, of learning, but then in the older participants, you almost see a subtle drop. So what I mean, this is an interpretation and speculation, but one possibility is that they're actually reducing their performance in the adult group. So whereas the 17 and 18-year-olds might be kind of maxing out what they can do, we see in the 19 to 20-year-olds that they're actually doing the best they can do in the high, but then kind of dropping. So this would suggest a sort of selective, not quite decision, but selective execution of when to exert effort.
Yeah, that's really interesting. Yeah, I kind of wonder. I mean, I know that you had some of the follow-up work that was looking at how these monetary values are indeed being represented equally across these age groups, but I don't know if beyond that follow-up analysis, if there was anything else that kind of looked at. I mean, I just I think of myself as a reference, right? Like when I was 13 or 14, my parents provided me in every possible way. Very fortunate in that capacity. But I kind of wonder, if over time, when people are moving out of the house, or suddenly they're in charge of their own paycheck, if there's some kind of other differences that are happening with money specifically that might be related to this.
So we have we try to get as much information from our participants as possible. So the mediation reflects socioeconomic status. We also have people give us information about the type of access to earnings that they have in their daily lives. So we ask kids if they get an allowance or chores, and college students give us a sense of do they have a campus job or do they have spending money. just to try to get a sense of how people are encountering this incentives in their daily lives. It really is impact. What's actually really cool is we have a paradigm in the lab just looking at how much physical effort people will exert. So we have them do a grip force paradigm where they have to it's actually really hard. I'm very bad at it, but they have to work to a certain level of physical effort to get rewards. And we see that even if you control for just strength differences across the age range, the younger participants are just as likely to physically work for the incentive. So we've done a lot of ancillary analyses to try to roll this out. I think there are, of course, like sociological factors. The thing that's actually really promising is that in these reinforcement learning studies, as well as in cognitive control tasks, you can change out the incentive structure and make it be points. You can have it be squirts of juice. You can have it be like pleasant pictures, and you see these same canonical effects. So I really do think there's like a context selective thing that's happening where they're representing the incentives relative to what they can get in the current task paradigm. And of course, there's probably things they're coming in with their outside world, but the hope is that we're controlling our experiments enough to look at that kind of selective difference to really tap into that.
I also have a question on slides like this. So I know you binned the ages for simplicity here, but you said you looked at it continuously. Is there anything like noteworthy with like how these ages are like tracked? Like for instance, is there an age cutoff that you notice where stakes benefits do start to emerge? Like, is there somewhere between 18 and 19 that it happens?
So that's a great question. Let me just see if I have the plot. Let me see if I can just pull it up. The regression line. And so you can see that there aren't confidence bands on it, so it's hard to see. But the emergence doesn't really become significant until around that 18-year age range. But there's not like an exact cut point. And I think so. The reason why we use continuous age as a predictor is because 18 doesn't mean adulthood. There's societal reasons that we call people above 18 or below 18 minors and above 18 not, especially when we're doing testing. And of course, there's lifestyle changes, but adolescence and adolescent brain development is an ongoing process. So what the continuous measures kind of not assume any type of boundaries on these developmental stages. And this is a linear fit, but we also fit nonlinear regressions using basically a type of a smoothing spline that would detect on where are things changing and how are things plateauing. And we see that this linear fit does a better job explaining the data than those kind of more flexible nonlinear fits. So it does seem to be this sort of late adolescent emergence. I don't think there's like an exact year or time. There's more of like a zone of significance, because also when we sample our participants, we use like 18.2, 18.4 as measurements, but we only have the precision up until the kind of the month or day, and based on the sampling of our participants as well. But you do see this emergence kind of really come online around here. Where would I have? Oh yeah, here, around here. Any other questions?
I feel like I just thought of a question and then immediately forgot it. Let me think for a moment. Oh, yeah, so I'm kind of curious if, what do the future directions of this line of work kind of look like, and specifically, what kind of individual differences may impact the degree at which we see these developmental changes. So I don't know if you've looked at any of that already or if you're planning to look at it, but I'm very curious about that.
So even though we have 84 participants, we're still not super high powered to detect individual differences. So we optimized the study to have age sampling, like kind of really filling in across our range, but this particular study isn't able to have that kind of fine range detection. But Leah is actually in the process of collecting an extension of the Human Connectome project, where they're having participants do tasks with different types of monetary incentives at stake, as well as perform different types of cognitive tasks. There's some carryover between like valuation as well as value-based cues in a subsequent go, no go. And that is a study, I think they're testing like over 1,500 participants between the ages of 6 and 30. I can't, don't quote me on the age range, but the goal of the study is to really get a sense of the normative population and not just age-related change, but differences in socioeconomic status, puberty. So they're collecting all sorts of pubertal hormones to get more traction on what are kind of the environmental factors or different developmental trajectories that can give rise to either earlier or later onsets of these phenotypes. So that's one line of work that's more in the individual difference arena. In my own personal work, I'm currently working with Wouter Cole, who is a postdoc with Sam Gershman and Byron Cushman, and we just got a grant to look at the more computational foundations of these decisions. So he's developed a task where participants do different types of learning for low and high stakes incentives, but there's also a cognitive effort manipulation. So sometimes one learning strategy is more difficult, but if you do it, it's better because you get more pay. But there's other situations where you a cheaper, less costly learning strategy. And what he's found is that in adults, they will use this costly, effortful strategy only when there's high stakes incentives. But if there's low stakes incentives, they kind of tend to rely on this easier computation. And so what we're going to do is test this in adolescents. And what this will kind of get at is, are adolescents making an effort judgment? Because on the one hand, they could just be doing like the hardest thing all the time. But on the other hand, they might just be doing the easiest thing all the time. So this will give us more traction on sort of like what's that effort computation that's changing with age as participants kind of either show this difference or don't show this difference in performance.
It's really interesting. I look forward to reading about it.
Well, we just got the grant, so
we'll give it a couple years. Yeah.
Yeah, I mean, it's again exciting. So it's more thinking of cognitive effort as sort of like a cost-benefit decision as opposed to just some.
So I actually have one other very low-level question, and as I look around, I know a couple of us work with children and adolescent populations, and so I'm just curious, what your lab's protocol is like for and just trying to reduce motion as much as possible and keep them calm and quiet while they're in there.
Yeah, so it's definitely it takes a lot of training. And so it simulates the environment very, very closely. So they go into a simulated board. We have them look at a screen with a similar setup where they're looking at the screen reflected in the mirror. And we also give them an accelerometer that's linked to a video. So we'll have the kids watch Kung Fu Panda, and if they make a movement, the video will stop for 5 seconds. And so the reason why this is nice is it's giving them immediate feedback. Because sometimes you can tell people, oh yeah, you're moving, but it's really hard to instruct that. And so what we'll do is we'll train them maybe on like 3 millimeters so they see what that's like, and then make it smaller and smaller and smaller. And this is like a really nice way to give them, it's like incremental learning. So they have this like physical sensation. The other thing we do is I didn't do it for these studies, but the Human Connectome Project is using a software program called FIRM. It's like FIRMM, that was put together by Nico Dosenbach and others at WashU. And what this lets you do is it lets you look at motion live, like on the fly. And so instead of waiting until after a run finishes or checking in after the fact, you can actually monitor motion as it's happening to give participants feedback. So we find that giving them feedback after every run is really helpful. I think the longer a scan is just like inevitable to some regard, but we've really gotten a lot better. So my first study, you may have noticed that we had to drop like 15 people because of motion. With this study that we ran most recently, I just had to drop 1 person. So I think our training is working, but it does take a lot of time, and it's definitely like we have people come in for an extra day, and it's something that we're really vigilant about, but it's made a huge difference in our data quality. So I think it's totally worthwhile.
So just a quick follow-up. So how long are they actually doing that training task? Is it like for the full length movie, or is it a subset of the movie?
So, but usually like 20 minutes.
Okay. Okay.
More just a demonstration of what it's like.
So still, if it still would be possible to do that same day of scan theoretically.
Yeah. I think the reason why we have people come in a little bit earlier is just to see if they're claustrophobic.
Okay.
So if they are, we won't have them go on the scanner.
That's very clever. Thanks so much for the insight. Other questions for Katie? All right, well, I think that's all we have for you. Is there anything that you have for us?
No, thank you so much for having me. And I'm sorry for the technical goof ups, but it was really great. And this is a really nice way to sort of interface with you guys from across the country. So thanks for the opportunity.
Thanks so much for joining us today, Katie. And good luck with your defense in the near future. Bye.
Bye.
All right. Well, we have just a few minutes.